So this is the second example to 2.4 on the precise definition of a limit. So the question is saying find delta, which is the distance from x to my value, such that if the absolute value of x minus 1 is less than delta, then the absolute value of x squared minus 1 is less than 0.2. So a couple of things. The x value is 1 here, and I'm trying to find the distance from 1. How far away from 1 do I have to be so that the function differs by 0.2? What's the function? Function is x squared here. And what's the y value, or what's the limit, would be 1 here. Okay, so graphically, it's x squared. There's x squared. And x is 1, y is 1. We know that. There's the point on that function. And I want to know how far away do I have to be so that the y value differs by less than 0.2. So if I come up here, that means I would be going to 1.2, and down here I would be going to 0.8, and I want to know what are the x values that correspond with those y values and how far away from 1. So two ways you could really do this now. I could just, once I understand what the problem's asking, I could just solve this absolute value inequality, and I could get my values, or I could set up the two equations on the right. So if I do it with the absolute value inequality, I would say x squared minus 1 is less than 0.2, and x squared minus 1 is greater than negative 0.2. And then I would just solve each, guys. I'd say x squared is less than 1.2. I'd take the square root of that, and I would get x is less than 1.1, rounding. Over here, I would add 1. I'd get 0.8. Take the square root of that, and I'd get 0.89. Now, what do I do with this? Well, I need to know how far from 1 I am. So now, interesting, over here, 1.1 to 1 is 0.1. And on this side, it's 0.11. So the distance on the left came out to be 0.1. So this distance is 0.1, whereas over here is 0.11. If that happens, I always take the closer, so take the smaller, which would be 0.1. So my delta value would be 0.1. Because as long as I am 0.1 away, my y value will differ by what? By 0.2. Okay, that's all we're saying.